Hello, welcome to this video, produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This one is in the second series on impulse or momentum and focuses on Newton's law of restitution. Collisions, the story so far. In a collision between two objects, we discount external forces acting. That's equivalent to saying that the collision is so rapid that they don't have time to make any significant impulse. We also suppose, essentially, to idealize that the collision takes place instantaneously, but in such a way that it allows one body to have an impulse on the other, and that those two impulses are equal and opposite. And as a result of that, we can say that momentum is conserved. We need more than that. We need to consider now elasticity. To build elasticity in, we need to use some observations from experiment, usually attributed to Newton. And Newton's experimental law, it says that if you take measurements, the separation speed divided by the approach speed is a constant. If it's a constant, we need to give it a name. It's usually denoted by the letter E, and it's called the coefficient of restitution. In effect, it's a property of the pair of materials which form the two bodies in collision. So we've got our definition of E. We also note that two things: that it's dimensionless, it must be because it's a ratio of two speeds. In effect, the units would cancel out. And E always lies between 0 and 1. Those two special cases, 0 and 1, have names. If E equals 0, the collision is described as totally inelastic. That's where the separation speed must be 0, so the bodies essentially stick together or coalesce. If E equals 1, then that case is called that of perfect elasticity. Let's take a simple starting case. Notice the usual schematic description of what's happening. We've got an approach velocity for A of 5 and a rebound velocity of 1, and similarly numbers for B, and we're trying to find E. As usual, if the numbers have no units, we take it that they're the standard units, so that for the approach velocity of A, that's 5 meters per second. So we look at the separation speed over the approach speed. Remember to get the fraction the right way up. Now the separation speed will be 4 minus 1 if you consider the directions, or perhaps it's intuitively obvious that it's 5. So it's 4 plus 1 over, and in the same way it will be 5 plus 2. So from that calculation we can see that E is 5 over 7. So there's a summary of the calculations, and we answer the question in the terms in which it's set. Notice that there are no units because E is dimensionless. Let's look at a second example. This time we're given the coefficient of restitution, and we're going to work out what the velocity is. If we don't know what the velocity is, we don't actually know which direction it's going to be, though we may have a hunch. If we turn out to have got it wrong, so long as we apply a set of signs consistently, it will turn out to be negative. So in this case, 3/4, our coefficient of restitution will be equal to the separation velocity, 4 minus v. You'd expect, if it's a collision, that 4 is going to be bigger than v, so there's your separation speed, and it's divided by the velocity of approach, which is 6 plus 2. So we have an equation, 3/4 is equal to 4 minus v over 8. So if we multiply both sides by 8, then we'll end up with 6 is equal to 4 minus v. And so that tells us that v is equal to minus 2. So our conclusion is that the diagram was indeed wrong. It's going in the opposite direction, and we need to make certain that's clear in our answer. So there we are. Our algebra gives us v is minus 2. And we summarise our answer by saying A rebounds. That implies it's changed direction with a speed of 2 meters per second. Now let's take a more general situation where we don't know either speed after the collision. So we allow a moment to read through the information to check that it is summarised correctly on the diagram. Mass A 4 kilograms, mass B 3 kilograms. The approach velocity of A is 4 to the right, and well, on the diagram it is, and for B towards A it's 6 to the left. So in order to solve this, we need to bring in some letters to represent what we're trying to find. So let's say V1 and V2. Now we have two unknowns, so we need two principles to apply. The first principle is the the restitution law involving the coefficient of restitution, and the second is the conservation of momentum. So we have 2/5 is equal to the velocity of separation v2 minus v1 divided by the velocity of approach, which is 10. So if we multiply both sides by 10, we'll end up with 4 is equal to v2 minus v1. We can't do any more with that because we have two unknowns. But we can apply the momentum law. Momentum before is equal to momentum afterwards. So reading off from above, we're going to have 4 times 4, but minus 6 times 3. That's the momentum before, and that equals 4 times v1 plus 3 times v2. Now that's our second equation, so we can see 16 minus 18 minus 2 is equal to 4v1 plus 3v2. So those two equations solved simultaneously will give us our solution. So there we are, our two equations. There's the first one and there's the second one. If we take the first one and rearrange it to get v2 is equal to 4 plus v1, and then substitute it in the second one will be minus 2 is equal to 4v1 plus 3 times 4 plus v1, and then we can solve that to get minus 2 is equal to 4v1 plus 12 plus 3v1, which will then tell us that minus 14 is equal to 7v1. So our conclusion is that v1 is equal to minus 2. That means that our diagram is incorrect. Our hunch that A moves to the right proves to be wrong, but that shouldn't discomfort us at all. The signs consistently applied simply bring us to that conclusion. So there we are. We've got v1 is minus 2, and if you put that back into the v2 equation, you end up concluding that v2 is equal to 2. So we can summarize our conclusion by saying that the 4 kilogram mass rebounds with velocity 2 meters per second, and the 3 kilogram mass rebounds with 2 meters per second. Somehow the answer must make clear what the direction is, and it needs to be referred in terms that make sense in the original question. So there we are. That brings us to the end of the video on Newton's law of restitution. The next one is in the same series, Impulse and Momentum, section 2, and it's about the loss of energy as a consequence of impacts involving restitution and momentum.